Hello everyone and welcome to lecture 40 of analog integrated circuit design. In the previous lecture we looked at the advantages of fully differential circuits, that is where every signal is carried on two wires and the two wires carry equal and opposite voltages with respect to ground. The main advantage is immunity to interference as well as that they cause less interference. They are immune to both stray interference from other wires that may be passing and also interference due to voltage drops on power supply and ground lines. Okay. So, we would like to make all the circuits that we have already made fully differential, that is the op amp and the transconductor and so on, and that we will look at in this class. Now, in the previous class we also saw how to analyze fully differential circuits. We can do that using common mode and differential mode half circuits. Now, as far as noise is concerned, if you take a single noise source, the circuit is not symmetric, but we can represent that as a combination of common mode and differential noise voltages. The common mode noise has no effect and the differential noise will have some effect. And finally, we found out that to calculate the output noise of a fully differential circuit, we can take the corresponding half circuit, do its noise analysis as though that were the entire circuit and double the voltage noise spectral density. Okay. Now, we will quickly look at how to calculate the offset in a fully differential circuit and then move on to design fully differential op amps. Now, we saw that if you have a fully differential circuit such as the differential pair loaded by resistors, the differential noise voltage between these two nodes will have some spectral density SVO. Okay. Now, we take the half circuit and calculate its output noise voltage spectral density. Let me call it SVO half. SVO will be 2 times SVO half. Okay. Now, as I emphasized, the noise current of this resistor causes a certain output voltage here and there, and similarly this resistor will cause some voltage here and there and so on, but the net result is that you take the half circuit, do its own noise analysis and double the spectral density to get the output noise spectral density in a fully differential circuit. Okay. Similarly, as far as the offset is concerned, let us consider the offset here. The offset in presence of mismatches will be some DC voltage VOS, and here I am calculating it at the output. It can be referred to the input by dividing by the gain. Okay. So, that is the output offset. Now, can we calculate that from the single ended equivalent circuit? Now, it turns out that we can. First of all, we simply insert the mismatch between transistors 1 and 2, that is the transistors corresponding to this single transistor in series with the gate of M1. Now, if we have some current mismatch that can be inserted here. Here delta ID12 is the absolute mismatch in the absolute current, and that is equal to I naught by 2 times delta beta. Delta beta is the mismatch in current factor between these two. There is no threshold voltage mismatch. The current mismatch in the between the two transistors would be simply the quiescent current times the change in beta value. Similarly, the effect of any mismatch in the resistor, okay, can be also represented by an equivalent current source or a voltage source. So, the mismatch current will be equal to the quiescent current flowing in the resistor, which is in this case I naught by 2. Let me assume this current is I naught times the mismatch in the resistance. Okay. Now, what will be given will be delta beta by beta and delta r by r and so on. For beta and r and so on, we specify the relative mismatch. From that we can calculate delta beta and delta r and multiply that by I naught by 2 here and there to get the equivalent current sources. Okay. Now, how can it be represented by an equivalent current? This comes from a simple application of substitution theorem or what is known as compensation theorem. I will not go into the details, but the mismatch in every component can be represented like this. So, finally, because of all these voltages, the small signal output voltage will be of some value. Okay. Let me call that VO as half. Okay. Now, it turns out that the variance of the output offset in the differential circuit exactly equals the variance of this output voltage we get in the half circuit. Okay. Now, in case of noise we get a factor of 2, in case of offset we do not get that, because this offset already represents the relative mismatch between two identical devices. It is assumed that this delta VD12 represents the mismatch between M1 and M2. Similarly, delta ID12 represents the mismatch between current factors of M1 and M2. Similarly, this delta R is not just the error in the value of R compared to the nominal value, but the mismatch between, if I label these R1 and R2, R12. Okay. So, because of this we do not get the factor of half, and this is the way the mismatch is normally specified. The process people measure a large number of pairs of identical devices and characterize the mismatch between them. Okay. So, what you have in the process data sheets is the mismatch between two nominally identical devices. So, again by simply doing the half circuit analysis you can find out the offset voltage. We considered the design of op amp in some detail. The op amp had a differential input and a single ended output. We needed the differential input to take the error between the desired and feedback signals, but the output was single ended with respect to some ground. Now, what we would like to is to move on to fully differential op amps, because we have already seen the advantages of fully differential signals. This is a single ended op amp. This is the input voltage and that is the output voltage, and in the small signal regime it is some DC gain times Vd if Vd is a DC. Now, what is a fully differential op amp? The input is differential and the output is also differential. The difference voltage, let me call it VO, and each of the individual voltages with respect to the ground would be some VCM plus, let me call it VOCM to denote that it is the output common mode voltage, plus VO by 2, sorry, this is the negative output. So, it is minus VO by 2 and this is VOCM plus VO by 2. And what is VOCM? It is the common mode of the output, it is usually some constant DC quantity, and that will be an input to the op amp. Okay. I will show it like this. So, you can specify the output common mode voltage of the op amp by providing a corresponding voltage to the op amp, and this voltage will be internal to the op amp. We will see how this will be used when we design this circuit at the transistor level. Now, how do we use this op amp? For example, we make an inverting amplifier like this one. VO is minus R2 by R1. Now, the fully differential version of this circuit would be Okay. The input is a differential voltage here and the output differential voltage will be minus R 2 by R 1 times V I. Okay. And I did not mention this earlier, V naught in this will be A naught times V d if V d is a DC, otherwise it will be A of s, where A of s is some transfer function, the transfer function of the op amp. Okay. So, this is the fully differential version. Again you can easily analyze that by assuming that the inputs of the op amp are a virtual short. If the op amp behaves like an integrator or if it has a very high gain, then these two inputs will be at the same voltage and the output will be minus R 2 by R 1 times V I. Okay. And if you look at the individual voltages, let me assume that the output common mode voltage is set to some voltage VOCM. This will be VOCM minus R 2 by R 1 V I by 2, and this other side will be the same thing except with a plus sign. Okay. So, the output will be fully differential. So, this is how you make fully differential circuits. Now, also please note that once you have a fully differential circuit, this minus sign loses its significance. Okay. If I measure the output voltage with the upper terminal being positive and the lower being negative, I get minus R 2 by R 1 times V I. If I flip the notation of V naught, I will get plus R 2 by R 1 times V I. So, simply by flipping the wires, I can get either positive or negative gains. So, that is actually a simplification in the realization of differential circuits. There are many occasions where when you make a single ended circuit, you need to realize gains of minus 1 simply to invert the polarity of the signal, whereas in a differential case you can invert the polarity of the signal by simply crossing the wires. Okay. Now, how do we come up with fully differential circuits? For any circuit with op amps which has one of the input terminals of the op amps to be ground, it is very easy. Let me just show the inverting amplifier example again, but I will show impedances just to make it look more general. So, we have this. Now, let me copy over and draw the same thing upside down. Okay. Z1, Z2. Now, these are two single ended circuits. If I have Vi by 2, I get Vi by 2 Z2 by Z1, the negative of that, and if I have minus Vi by 2, I get this voltage at the output. Okay. Now, these two voltages are connected to ground. Now, you see that there is a virtual short between these two terminals and these two. So, effectively the voltage at that and that point are the same if the op amps are ideal. So, what we do with the fully differential op amp is to essentially lift this off the ground, that is ignore this part and have only these parts of the circuit. Okay. The total input voltage will be the total difference voltage here Vi, and the total output voltage will be Vi times Z2 by Z1. Okay. And I will not always show this explicitly, but the output common mode voltage is set to some VOCM. This means that the two output voltages will be VOCM plus Vi times Z2 by Z1 by 2 and VOCM minus Vi times Z2 by Z1 divided by 2. Okay. So, this is quite easy to do for any circuit in which the op amp has one terminal to ground. Okay. If the op amp does not have either terminal at ground, you cannot do this, but usually we can make all the circuits that we want with circuits of this type. So, we will not worry too much about that. Okay. Now, how did we make our single ended op amp? With a certain unity gain frequency omega u, we used a transconductance or a voltage controlled current source GM and passed its output current through a capacitor C. Okay. Now, when we want to make a fully differential op amp, the principle is the same. Let us say the unity gain frequency is omega u, then the total output voltage will be omega u by S V d of S. That is what we would like ideally. The op amp is an integrator. What we need in this case is a fully differential transconductor, and what is the meaning of that? If I apply a voltage V d, there is a terminal at which it draws a current G m times V d, and there is a terminal where it pushes out a current G m times V d by 2. Okay. And you pass each of these currents through capacitors C, then the output voltage will be G m by S C times V d of S. Of course, the unity gain frequency of this op amp is G m by C. Okay. So, first of all we need a fully differential transconductance G m, and we need 2 capacitors, and this is always the case. The physical structure, the schematic of a fully differential circuit will be symmetrical, it has to be. Okay. We need 2 integrating capacitors C. Okay. How do we realize a differential G m? It turns out we can do it in a very similar way that we realize the single ended transconductance. If you take a differential pair, and apply a differential voltage to it, what we get are incremental currents which are equal and opposite. Okay. So, here we get a total current of I naught by 2 plus G m V d by 2, and here it is I naught by 2 minus G m V d by 2. Okay. Now, this is exactly of the form that we require here, except that there is also the bias current I naught by 2. So, if we subtract off the bias currents I naught by 2 from these 2 arms, what will be drawn from here and what will be pushed in out of that node will be G m V d by 2. So, this is exactly the circuit that we require. We need a differential pair and we need current sources I naught by 2. Okay. So, what is the difficulty? Now, we can try to implement this directly, but so let us say I take 2 PMOS transistors and bias them with a current mirror. Okay, let me assume these transistors are all identical. Okay, M3 prime, M3 and M4. and bias them with I naught by 2. What will happen? It is very easy to see when I make the common mode half circuit of this, that is I take this half of the circuit and fold it over the other half. Okay. Let me assume that there is no signal at this point. Now, clearly you see that this is like having two current sources that are connected together. Okay. Nominally this current source equals I naught, that is the current in M3 and current in M4 put together, but in general it will be something else. Okay. I will call it I34, and if I34 is different from I naught, either this voltage will keep on rising until M34 goes into triode region, or it will keep on falling until M12 and M0 go into triode region, right. So, this you recall, it looks like having two current sources I34 and I naught like this. We know that with ideal current sources we cannot even make this connection unless I34 happens to be exactly equal to I naught. Now, there is no way to guarantee that the total current from the upper transistors M3 and M4 equals the current from the lower transistor M0. Okay. So, if you do build this circuit, you will almost certainly find the output to be very close to the VDD rail where the PMOS transistors are in triode region, or very close to ground rail where the NMOS transistors are in triode region. Okay. So, we can't do this, and we also know from biasing circuits, that is where we bias the transistor at a given bias current I naught, that we will never be able to set the two current sources independently and have their values to be equal to each other. The only way to do it is by setting one of them using negative feedback. Okay. For instance, we can adjust the gate voltages of M3 and M4 such that their total current output equals the current of M0, and we have to do this with negative feedback. Okay. So, let us see how to do that. So, like I said, what happens is, if the total current in M3 and M4 is larger than the current from M0, these voltages will keep on rising. Okay. Now, if the total current is smaller, these voltages will keep on falling. What I want is for the sum of these two voltages to be some constant, okay, such that all the transistors M1, M2, M3, M4 are in saturation region. So, let me call this VOP and VOM. Okay. I can't use this kind of biasing, this has to come from feedback, okay, which is usually called the common mode feedback or CMFB. Now, what should this feedback be based on? It should be based on the average value of VOP and VOM. Okay. We do not want to react to VOP and VOM individually. Like I said, we need an op amp, and the op amp's output must be able to vary. Okay. It is not that the op amp's output voltage must be fixed, then the op amp is completely useless. What we want is that the average of the two output voltages be equal to some constant VOCM. Okay. These two voltages have an average or a common mode value equals VOCM. So, what should I do? In negative feedback, as usual, I have to compare the actual value with the desired value and adjust the actual value until it becomes equal to the desired value. Now, here what is the actual value? That is the output common mode voltage of the op amp. Okay. I need to detect the output common mode voltage. Let me call this the common mode detector. Okay. So, its output voltage will be nothing but VOP plus VOM divided by 2. Okay. Then I have to compare it with the desired output common mode voltage VOCM and feed it back to the gates of M3 and M4 in the right direction. In the right direction means that if the output common mode is too high, what should happen is that what that means is that the current in M3 and M4 are lower than the current from M0. Okay. So, then the current in M3 and M4 must decrease. Similarly, if the output common mode voltages are very high, that means that the current in M3 and M4 is more than the current from M0. So, the current in M3 and M4 must decrease. Okay. So, when the current in M3 and M4 decreases, VOM and VOP will be pulled down. Similarly, when this output voltage is too low, the current in M3 and M4 must increase, so that the output voltages increase. Okay. So, you will see that to decrease the value of the currents in M3 and M4, we need to increase the output voltage. So, if the voltage is very high, the common mode feedback voltage must be increased. If the output common mode voltage is very low, the common mode feedback voltage must also be decreased. Okay. So, the polarity of the op amp used in the common mode feedback is given by this. Okay. You can also determine the signs by breaking the loop and making sure that what comes back is negative and so on. Whatever I described is just that, what in different words. So, this is the general common mode feedback circuit. You need to have a common mode detector, so that you detect the actual output common mode voltage. You compare it with the desired common mode voltage VOCM and you control one of the current sources with it. Okay. In fully differential circuits, you will always have scenarios where you have some current source coming from the top and something coming from the bottom, and the two have to be made exactly equal. And the way to do that is to control one of them using negative feedback. Okay. Now, we will see how to implement this negative feedback. There is a wide variety of common mode detectors as well as ways to close the feedback loop. Okay. First of all, let us consider common mode detectors. We want to take in VOM and VOP and obtain an output VOP plus VOM divided by 2. Okay. How can we do this? The simplest way of getting the average of two voltages is to use a resistive divider VOP and VOM. So, we will get VOP plus VOM by 2, okay, if these two resistors are equal. So, that is a potential candidate for the common mode detector. So, let us use that here. We will see what the implication of this is later. Let me label these gate voltages VG34. The next thing is how to close the feedback loop. Okay. As I said, if the detected common mode voltage VOP plus VOM by 2 is too high, that means that the current in M3 and M4 is too high, and we have to go on increasing the value of VG34. So, that the current in M3 and M4 goes on reducing and the output common mode voltage reaches the desired value. Similarly, if the detected common mode voltage is too low, you have to continuously reduce the value of VG34, so that the currents in M3 and M4 will increase and the output common mode voltage reaches the desired value. Okay. and vice versa. Now, there are many ways of completing the loop. We can use an integrator or an op amp between this point and that point, so that we get the feedback action that I just described, but the most simple realization of this is to observe that if VOP plus VOM by 2 is too high, VG34 also must increase, that is, it must go in the same direction as VOP plus VOM by 2. Similarly, the incremental gain required from this point to that point is positive. Okay. So, as you can see here, if this voltage is detected common mode is too high, the common mode feedback also must be high. Similarly, if this is too low, the common mode feedback also must be low. Okay. And the simplest way to arrange that is to connect the two together. Okay. Now, if you recall how you derived the diode connected transistor, where the transistor is biased at a constant current, we detected the current difference at the drain and fed it back to the gate. There were many ways of feeding it back, but the simplest realization was to tie the gate to the drain. Okay. Now, this is similar, but in this case it is not a single transistor. We detect the common mode voltage of the two transistors and connect it directly to the gates of the two transistors. Okay. Now, you can analyze what happens. First of all, let us assume that there is no differential input. Okay. In that case, these two voltages have to be equal to each other by symmetry. So, no current flows through R, and this voltage equals the output voltage VOP plus VOM by 2. Okay. Now, when the feedback circuit is settled, the current in this has to be I naught by 2 and the current in this is also I naught by 2. Okay. And also the gate voltage of this equals the voltages at the drains of M3 and M4. Okay. So, the output voltages will be equal to VDD minus VSG of M3 or VSG of M4 at a current of I naught by 2. It has to be equal to this. If this voltage is higher than that, that means that the current here is too low and the voltages VOP and VOM will be pulled down. If this voltage is lower than what I mentioned here, then the current in M3 and M4 is higher than I naught by 2 and these voltages will be pulled up. Okay. So, in this case the output common mode voltage will get stabilized to this particular value. Now, in this this is nothing but the output common mode voltage VOCM. In this particular circuit, we did not provide a VOCM from outside, it is built into the constants of the MOS transistor. Okay. So, once you have the threshold voltage and the current factor and the current values, you can calculate the output common mode voltage. Okay. This is VOCM. Now, we do not have freedom in setting the VOCM arbitrarily, it depends on the threshold voltage and the parameters of the MOSFET, because VSG3 is nothing but the threshold voltages of the PMOS transistors minus square root of 2 times I naught by 2 divided by mu p Cox W3 by L3. Okay. Now, by choosing the dimensions of the transistor, you can play around a little bit with the output common mode voltage, but you do not have too much freedom to do so. Okay. But in many cases this circuit works perfectly well. Now, what happens if you apply a differential input? Now, let us say I have plus Vd by 2 and minus Vd by 2 here. What happens in that case is that there will be an incremental voltage VOP and an equal and opposite incremental voltage in VOM. Okay. Now, because the voltage at this node is the average of the two voltages and the increments are equal and opposite, the voltage VG34 does not change at all. Okay. VG34 does not change if you have a fully differential input. Okay. So, what does that mean? That it means that M3 and M4 will continue to supply the same current as before, and the differential current, the extra current that is drawn from M1 and the extra negative current that is drawn from M2 will flow through R. Okay. So, there will be a current GMVD by 2 in that direction. Okay. So, the upper transistors M3 and M4 behave like constant current sources, and because of negative feedback their sum is adjusted to be exactly equal to the value of the tail current source I naught. Okay. And we need the negative feedback because there would be no other way to adjust their values to be exactly equal to the tail current source. So, a fully differential op amp needs common mode feedback. Okay. And another way to think about it is that we really have two output voltages in a fully differential op amp, okay, the positive and the negative output voltage, and we need two feedback loops to fix the individual voltages. Now, as usual it is better to think of differential and common mode voltages instead of individual voltages, because what we desire is the differential voltage and what we want to suppress or what we want to hold constant is the common mode voltage. So, this kind of an op amp any which way you think about it needs two independent feedback loops. Now, we do not think of it as two independent feedback loops controlling each output voltage, we think of it as one feedback loop controlling the differential output voltage. This is the feedback loop that controls the functionality. Okay. So, if you look at this particular circuit in the single ended case, the feedback loop formed by the impedances Z1 and Z2 control the output voltage. Similarly, here the feedback loop formed by Z1 and Z2 control the differential output voltage. Now, we need another feedback loop, and that feedback loop operates only on the common mode output and it helps set the common mode output voltage. Okay. Now, what is the effect of the common mode feedback on the differential circuit? We added some components here and we have to investigate what its effect is. Let me redraw the circuit. Okay. This is my fully differential op amp or the simplest realization of the fully differential op amp, and the differential half circuit is given by only one half of it by grounding all the nodes along the line of symmetry. This is the differential half circuit, and the common mode half circuit is obtained by folding the two halves together, which gives me M34 and R by 2 and M12 and M0, and here we just have V bias. Okay. This is small signal ground, and that is VDD. Okay. Now, first of all, in the differential half circuit, what we wanted was only this M1, which is the transconductance, and M3, which is the load conductance or the load current source. Now, we see that we also have an extra element which is R. Okay. What is the effect of that? It is very easy to see. The R here appears in parallel with the GDS of M3 and GDS of M1. Okay. So, the voltage gain from this point to that point will be the GM of transistor M1 divided by GDS1 plus GDS3 plus this conductance G. Okay. Just to make it explicit that we put it there for common mode feedback, let me rename that RCM, and the reciprocal of that is GCM, and you can see that this GCM reduces the DC gain of the op amp. Okay. Normally, we would have got GM1 by GDS1 plus GDS3, which by the way is exactly the same gain that we get for a single ended single stage op amp. Okay. Now, one thing you also notice is that the analysis of DC gain in this case, the fully differential op amp, is a lot easier than what we had to do for the single ended op amp. This is because the half circuit concept makes it very simple to analyze. Okay. We have only 2 transistors here with a resistor, and by inspection we can write down the expression for the gain. Okay. Now, this common mode detecting resistor, the resistor RCM used in the common mode detector ends up reducing the gain. So, you have to use as high a value as possible. Okay. You have to make this to be as high as possible. Now, just for completeness, let us also look at the common mode half circuit shown on the right side. Now, you see that this M34 is diode connected with a resistance R by 2 in the feedback loop. Now, because the gates do not carry any DC, it makes no difference at all to the DC picture. So, this makes the connection of this type of common mode feedback circuitry to diode connection very explicit. Okay. Now, in this case, in the common mode picture, you see that you have a current source I naught, which is pumping a current into a diode connected transistor M34. So, the current in M34 will be set to a value equal to I naught, it is quite obvious. Okay. If we did not have this feedback loop, the current in M34 could be different from I naught, and this voltage would either rise or fall, but now it will be set to a value equal to VDD minus VSG of M34. Okay. Now, this brings us to another way of thinking about common mode feedback circuits. I just now said that we need to stabilize the output common mode voltage as well. Now, this is like having to stabilize 2 output voltages, but instead of stabilizing the 2 output voltages separately, we stabilize the differential output using the differential feedback loop, which determines the function of the circuit, and we set the output common mode voltage to a constant value using the common mode feedback circuit. Okay. Now, another way to think of the common mode feedback circuit is as follows. First of all, when we had only a differential pair, with resistive load, now what happens is that the output common mode voltage gets set to VDD minus I naught R by 2, where this is the current I naught. Now, there is no problem at all setting the output common mode voltage. Okay. It gets set to VDD minus I naught R by 2, whereas if we replace the resistances by current sources, with some bias here, we will not be able to tell what the output common mode voltage is. Okay. What is the voltage here? We will not be able to tell, because small differences in the current in the upper transistors and the current in the lower transistor I naught will cause these voltages to go up or down severely. Okay. This is because as long as the load resistance is rather small, the output common mode voltage will be set very accurately, whereas if the impedance of the load becomes very high, as in a current source, there is a lot of uncertainty, because a small difference in current going into a large impedance can give you a large change in the output voltage. So, in a way, what the common mode feedback circuit is doing is shown in this figure on the right. It basically presents a small impedance in the common mode. Okay. in the common mode the transistor M34 is diode connected, okay, whereas in the differential mode you see that the gate of M3 is grounded. So, there is no feedback at all in the differential mode around M3. So, the goal of the common mode feedback circuitry can also be thought of as providing a load resistance which is very low for common mode and very high for differential mode. Ideally, the common mode feedback circuit should not affect the differential mode circuit at all, but in reality it does to some extent. As we see here, it presents a load resistance R. In the next lecture, what we will do is look at different kinds of common mode feedback detectors and look at some choices which will not affect the differential picture and consequently will not affect the differential gain. Okay. In summary, we need to have an extra feedback loop in fully differential circuits, that is to stabilize the output common mode voltage. Okay. Now, in order to do this, we need to be able to detect the output common mode voltage and feed it back to some current source. In general, in any high gain circuit, there is a current source on the bottom driven by the signal perhaps, and there is a current source on the top perhaps providing a constant current. Okay. This is invariably the case. If you go back to any of the op amp circuits we have studied so far, you will find that this is the case. Now, the need for current sources is obvious. They give you a very high incremental output resistance and consequently give you very high gain. Now, a very high gain also implies that the output voltage is very sensitive to small changes in current, that is the definition of gain in fact. So, if you do not match the upper and lower current sources accurately, the output common mode voltage will not be stabilized accurately. So, you have to stabilize one of the current sources using negative feedback. You cannot have two current sources in open loop, one on top of another. Okay. To do this, we detect the common mode voltage, compare it to the desired common mode voltage and feed it back to the common mode current sources. In the simplest realization, we did not do the comparison explicitly, we simply fed it back directly. So, the output common mode voltage will not be something that we set, but it is related to the properties of the transistor, but nonetheless that is how common mode feedback in general works. Now, the common mode feedback circuit provides a very low impedance in the common mode and very high impedance in the differential mode. In the differential mode, there should be no feedback at all if the common mode feedback circuit is designed properly. Okay. In our case, the common mode feedback circuitry is affecting the differential picture because the common mode detector is made using resistors. In the next lecture, we will see how to make common mode detectors which will not affect the differential picture. Thank you.